Hello, and welcome back to the course on Physics for Engineers. So we are still on the 12th chapter of this course, which is all about DC circuits. So for this lesson, this is now the heart of this chapter. We'll now be talking about DC circuits. But before that, let us first review what we have discussed in the previous lessons. So in the previous lessons, we have discussed about Ohm's law, the relationship between the voltage, current, and resistance in a material. And we also have discussed about resistor connections, series connections wherein the equivalent resistance becomes larger. And then you have parallel connection wherein the equivalent resistance becomes smaller. So for this lesson, we will be talking about direct current circuits and power. So I may have mentioned before in the previous lessons regarding what is a simple circuit. So it's basically the simplest complete circuit that can make, and basically all you need is a source of EMF such as a voltage source, such as a battery, and a resistive element, an element with a resistance such as a resistor or a light bulb. It's a resistive element, it has a resistance, or any electronic or electrical device. So those are just the two basic elements of a simple circuit. Of course, you can have other elements in a circuit. So this is the simple circuit. Say your source of EMF is a battery, and you have an electric or electronic device. So conventional current will flow out from the positive terminal of the battery, goes to the electric device, and then goes back inside the battery, and it will go on in a cyclic manner. So usually the wires that we use in our electrical circuit are metals, since they have very small or negligible resistance. So since it's as we have discussed in the previous lessons, in the examples, for a copper wire, its resistance for a 1 meter copper wire, its resistance is just in micro ohms, very very small resistance, and we can neglect those resistances. So a complete circuit is basically a closed loop. So that's if you have a complete circuit, a complete circuit forms a closed loop, such as this one. So there's a closed loop. If there is a gap in that loop, then that's an incomplete circuit, and direct current will not flow in an incomplete circuit. Okay. So these are the different circuit symbols. So if you just see a line, that's just a conductor, a wire with negligible resistance. If you have the zigzag symbol, so that's the resistor or any resistive element. And then if you have two parallel lines, but the length of the lines are not the same, this is the symbol for the source of EMF or the source of voltage. So if you will recall, for a capacitor is also two parallel lines, but they have the same length. But here, the symbol is two parallel lines but with different lengths, and the longer line is the positive terminal of the source, and the smaller length is the negative terminal. And this is our symbol for EMF. It's the Greek letter Xi, Xi, Greek letter Xi, but I will not call that by its Greek letter. I will just call that EMF. So this is an ideal source of EMF. A real source of EMF actually has some sort of resistance, internal resistance. So there's this is the symbol for the internal resistance. So a real battery, for instance, has an EMF, and it also has a real an internal resistance. So this is our symbol for a voltmeter, a device for measuring voltage. This is our symbol for an ammeter, a device used for measuring current in amperes. We also have an ohm meter for measuring resistance, and then but all of these meters are usually contained in just one device, in what we call a multimeter. or a multi-tester. If you have heard of that, multimeter and multi-tester or multi-tester, they can measure voltage, current, resistance, and even capacitance. Okay. So for an ideal source of EMF, such as this one, the voltage of this source is just equal to its EMF. But if you have a real source of EMF, the voltage of this source depends on whether there's current flowing through it. If there's still no current flowing through it, which means it's an open circuit, it's not a complete circuit yet, or it's not a closed circuit, then the voltage is just equal to the EMF. But if you connect it to a circuit and there's no current flowing through the circuit, it's now a closed circuit or a complete circuit, then the voltage will now become smaller. It will actually be subtracted by a factor of minus I, the current, times the internal resistance. So if you have a battery, for example, a 1.5 volts battery, when you measure it without connecting it to a circuit, its voltage will actually be higher, maybe 1.6 or 1.7 volts. But when you connect it to a circuit, its voltage will now be decreased by a factor of minus I times R. It will have an internal resistance, and that is and you will then measure. If you connect the battery to a circuit, then you will measure 1.5 volts if it's connected to a circuit. But if it's not connected to a circuit yet, it's an open circuit, its voltage is equal to its EMF, which is usually around higher than 1.5, 1.6 or 1.7 volts. So that one. So this is an open circuit. There's still no current because there's no closed loop. This is now a closed circuit because you now connect your battery to a resistive element. So current will now be flowing inside your circuit. And this is what we call a short circuit. As we have discussed in the previous example, if there's no resistance large enough to control the flow of current, then you will have a short circuit and there will be a very large current flowing through your circuit, and your circuit might blow up. Your battery might blow up, your wire may burn. And if you touch the wire, you might get electrocuted and you might die. So don't do a short circuit. Don't short circuit your batteries. So I have mentioned this earlier. Real batteries will have a lower voltage when connected to a circuit as compared to when it's not connected to anything. Okay, let's not discuss power in circuits. So basically, the power in a circuit is the electric potential energy used per unit time, and this is for a source of EMF. The power generated by a source is just the current flowing through the source times the voltage of the source. So the power delivered, on the other hand, the power delivered to a resistive element is just still current times voltage, current of the resistive element, current flowing to the resistive element times the voltage of the resistive element, or by Ohm's law, since V is equal to IR, so we also have I squared times R, the current through the resistive element times the resistance of that resistive element. So let's consider a simple circuit. So the voltage of this source is 10 volts, and then you connect it to a 10 ohm resistor. So this is a simple circuit. So V is equal to IR. So a current is basically just voltage over R. So 10 volts over 10 ohms. So there will be a 1 ampere current flowing through the system. So we consider this an ideal source of EMF. There's no internal resistance here. So meaning there's 1 ampere current flowing through the circuit. So 1 ampere times 10 volts. So the power generated by the source is 10 watts. So current is 1 ampere times 10 volts. So 10 watts. So the unit for power again is watts. So 10 watts. Now, the current now gains 10 watts of power from the source, and it will deliver that 10 watts of power to the resistive element. So when the current reaches the resistive element, such as an electric device, the current loses 10 watts of that power and gives it to the resistive element. And then the current has no longer power, and then it will again get power from the source, get 10 watts power from the source, deliver it to the resistive element, and then it will no longer have any power, and then it will get another power again to the source. So it's a repeating cycle. So that's basically what happens in a simple circuit. Current delivers power, and in relation, current delivers energy, because power is just energy per unit time. So current gains energy or power from the source, and loses because it delivers. It gives energy and power to the resistive element or to the electric device. So current delivers power and energy to resistive elements. So let's now consider a series connection. So as I've mentioned earlier, a series connection is a voltage divider, but the current is the same. So 1 ampere current still flows to the system because the equivalent resistance is 6 plus 4, 10 ohms, similar to the previous circuit that I have shown you earlier. So in this case, series and parallel connections are all power dividers. If you have a series or parallel connection, power is always divided. So there's a 10 watts power from the source. The current delivers gains 10 watts from the source. It delivers 4 watts for the first resistor, and then the remaining 6 watts is given to the second resistor, and then it will get 10 watts of power again from the source, deliver 4 watts for this resistor, and deliver 6 watts to the second resistor. So since the current is 1 ampere, you can solve for the power needed by this resistor. So I squared times R, 1 squared times 4 ohms. So 4 watts. It will get it will receive 4 watts from the current, and this one will receive 6 watts from the current. Okay, so 10 watts is divided into 4 watts plus 6 watts. That's for a series connection. For a parallel connection, sorry. So for our parallel connection, we have a resistor of 30 ohms and 15 ohms. If you add that one, the equivalent resistance of this parallel connection of 30 ohm resistor and 15 ohm resistor is 10 ohms. So this is an still equivalent to 10 ohms. So there will still be 1 ampere current flowing through here. But when the current encounters this point here, in which there are now 2 roads or 2 paths, so current will be divided. So a parallel connection is a current divider, but the series and parallel connections are all power dividers. But a parallel connection is only is a current divider. So current will now be divided. The 1 ampere current will be divided. So 1/3 will actually go here, and the 2/3 ampere will actually go here. And the 1/3 ampere that goes through here, the 2/3 ampere that goes through here will recombine again to become 1 ampere current here. And it will go again in another cycle. So the power delivered to this resistor here is 10/3 watts or 3.333 watts. And the power delivered to the resistor here is 20/3 or 6.666 watts, a total of 10 watts. So the current carries 10 watts. The current is split. So 1/3 of the current goes here, 2/3 of the current goes here, meaning 1/3 of the power goes here, 2/3 of the power goes here. And then the current goes out again to 1 ampere, gets another 10 watt supply, and then delivers it to the resistive element. So that's basically how power and energy is delivered to an electric device or electronic device in a DC circuit. So let's now have an example. So this is current in closed and short circuits. So find the current flowing through the closed and short circuits if the EMF is 3 volts and the resistance R is 10 ohms. And the internal resistance of the battery or the source of EMF is 0.1 ohms. Note that the internal resistances are usually very, very small. So usually, the internal resistance of any source of EMF, such as a battery, is usually very, very small. In this case, it's 0.1 ohms. So for the closed circuit, the voltage is the EMF minus I times R. So in this case, we need to solve for the current. So cross multiply I here, and then factor out current. So you have R plus R and divide by R plus R, and you will get this one. So EMF over capital R, the resistance of this resistor, plus the internal resistance of the battery. So 3 volts, then 10 ohms, 0.1 ohms. The final unit is amperes, so 0.30 amperes. For the closed circuit, there's a 0.30 amperes flowing through this circuit. Now, how about for the short circuit? So for the short circuit, there's no resistance, there's no load connected to the battery. So this term here is 0. So you basically just have the EMF over the internal resistance. So 3 over 0.1 amperes, or that is 30 amperes. And as I mentioned earlier in the previous lessons, 10 ampere will surely kill you. So definitely 30 ampere current will definitely kill you. So that one. So please don't. Again, I'm always reminding you this again and again in every lesson. Don't short circuit your batteries. So let's have another example. So this is actually the network of resistors in our previous lesson. And the equivalent resistance of this is actually 4 ohms. And we now connect it to an 8 volts ideal source of EMF. So we are now asked to find the power generated by the source and the power delivered to each resistor. So in the previous lesson, we have simplified this circuit into this one. So we combined R1 and R2 in series into just R12. And then R12 and R3 are in parallel. We combine that. There's an equivalent resistance for that, which is 1 ohm. And then the equivalent resistance is 4 ohms of the whole network of resistor, which is 4 ohms. So if you will notice here, the current that is flowing through resistor 4 and resistor 5 and resistor 1, 2, 3, the equivalent resistor R1, 2, 3, is just this current here. The whole current that's passing through the voltage, the source of EMF, our voltage source. So we can actually calculate that one, the current in I4 and I5. Since this is series connection, so the current that's flowing in R5 and R4 and R1, 2, 3 and through our voltage source is just the same, because this is a series connection. So I4 and I5 is just basically this one. We use Ohm's law in this circuit here. So the current here is just V over R, the voltage of the source times the equivalent resistance, which is 4 ohms. So Vs over voltage of the source over the equivalent resistance. So 2 amperes. There's a 2 amperes current flowing in this circuit. So 2 amperes current flowing through R5. 2 amperes is also flowing through R4. So I4 and I5 and I1, 2, 3, this is equivalent to 2 amperes. So meaning the power of the source delivered by the source, generated by the source, is current times the voltage. So 2 amperes times 8 volts, you will have 16 watts. So this is the power generated by our source of EMF, our voltage source. Now, for the power generated by, delivered to R4, it's just I4 squared times R4. I4 squared is the current through I4, which is just 2 amperes. So 2 amperes squared times R4 is 1 ohm. The resistance of R4 is 1 ohm. So you have 4 watts. So 4 watts of power is delivered to R4. So the same power is also delivered to R5. Since R4 and R5, I stand corrected. R5, the same current but different resistance. And R4 is 1 ohm, R5 is 2 ohms. So you will have 8 watts. So originally we have 16 watts. 4 watts is given to R4. 8 watts is given to R5. So how many is left from the 16 watts that is generated by the source? So you now have 4 watts left, because 8 watts is delivered here, 4 watts is delivered to R5. So we know that 2 amperes is flowing through R1, 2, 3. And we know the current that's flowing through R1, 2, 3, the equivalent resistance here. This is actually R1, 2 and R3 combined. That's 2 amperes flowing there. And the resistance of R123 is 1 ohm. So basically, we know V123, the voltage of this resistor here, R123. It's I123, 2 amperes, R123, 1 ohm. So you get 2 volts. So the voltage of this resistor is 2 volts. Now, since this is a composed of parallel connection of R1, 2, and R3, this means that the voltage of resistor R12 and resistor R3 is also 2 volts, because this is a parallel connection. Parallel connection is same voltage, so 2 volts. So we now know the voltage of this one. So we can now solve for the voltage of, for the power delivered or current delivered in V3. Since the voltage of resistor 3 is just 2 volts and the resistance of resistor 3 is 2 ohms, so we see that the current flowing through R3, resistor 3 is 1 ampere. And we can now solve for the power delivered to R3. It's 2 watts. Okay, so finally, for this resistor R12, which is just a series connection of R1 and R2, we can solve for the current flowing through this equivalent resistor here. Since we know that the voltage of this resistor is V12, 2 volts, and we know that its equivalent resistance is 2 ohms, so we know that the current is 1 ampere. The current that flows through R12, and meaning the current that flows through R1 and R2, that is 1 ampere. Take note, this is a series connection, so same current that flows through these two, R1 and R2. So it's 1 ampere. So we know the current, so meaning we can now solve for the power. Power is just I squared R, so 1 watt is delivered to R1, and also another 1 watt delivered to resistor 2 R2. So that one. So in order to solve for the power, in this case, you only need to solve for the current in each resistor, because power is just I squared times R. We already know the resistance, we just need to know the current. Okay, let's try to analyze this system. So R4, there's 2 ampere current here. 2 ampere current is also flowing through R5. And then through R3, it's 1 ampere. Through R1 is 1 ampere. And through R2, there's also a 1 ampere current. So you will notice here, there's a 2 ampere current. This is just a series connection, so it flows. 2 ampere current is also flowing here, making the power of the source 16 watts. So 8 volts times 2 amperes, 16 watts. And then 2 amperes is also flowing through R5. But when it hits this crossroads, basically, the 2 amperes is divided into 1 ampere flowing through this branch and the other 1 ampere flowing through this branch. But the 1 ampere flowing through this branch and the 1 ampere flowing through this branch recombine to form the 2 amperes flowing through the circuit again. So we'll actually generalize these things in the next lesson on Kirchhoff's rules to analyze the flow of current and the voltages in a circuit. So our source here generates 16 watts of power. It gives 4 watts to R4. It gives 8 watts to R5. And it gives 2 watts to R3 and 1 watt to R1 and 1 watt to R2. And still, the power and energy is conserved. 16 watts is generated by the source. 16 watts is this 16 watts is divided through all of the resistive elements in the circuits. Okay. So that ends our lesson on DC circuits and power. So in the next lesson, we will be generalizing how to analyze DC circuits, or actually any type of circuits, using Kirchhoff's rules. I will see you again in the next lesson.